Okay, last week here, 2 more lectures. So today we'll get into alkynes, their structure, and then some reactions. Not too much to cover that's different than alkenes, so we'll do some practice problems at the end. And you'll have your Module 5 exam on Wednesday, and then your final exam, I think, is next week. Can I narrow it down more than that?
It's Wednesday at 10:45.
So Wednesday, 10:45. Again, that's the ACS final exam. 70 questions, multiple choice, yeah. The final exam, you'll get a packet of 3 things. The first one is the exam. The second one is whatever form that uses, so that comes with it. And the third one is a piece of scrap paper. So it's like a Scantron, but it's, I don't know if it's better, but it's, I mean, it's fill in the bubble, but it doesn't look exactly like a Scantron. It's their own separate form or whatever. Those 3 things have a unique identifier in all of them. So you're going to get 3 things. You have to hand 3 things back in. You cannot leave here with any of those 3 things. Do not mark in those books because those books are reused. And the next thing is you have to use a pencil on that. If you use a pen, the machine will not read it.
Can it be mechanical pencil?
Any sort of H2B lead is fine. The other thing, it needs to have your ID on it. If you don't have your ID and those numbers bubbled in, then I can't put a grade in your Canvas for you. I'll have some more to say about that on Wednesday. Okay. So let's get into our last functional group of the semester here, alkynes. And the reactions are pretty much the same as alkene additions. They can do it twice, or they can stop at 1, just like an alkene. So alkynes are the last of our hydrocarbon functional groups. They have the carbon-carbon triple bond and therefore have 2 degrees of unsaturation. So in the progression from alkanes to alkenes to alkynes, we're successively removing an equivalent of H2. And so each time you do that, it increases the degrees of unsaturation. In terms of the acidity of the CH bonds, for alkanes, we have sp3 hybridized carbon H, so those are the weakest acids. They have a pK of 50. sp2 hybridized CH is 45. And then there's a huge jump to when it's sp hybridized. And so the reason that is relates to the percent S character. So for a sp hybridized carbon H bond, percent S character is basically looking at how much of that spherical orbital contributes to the hybrid orbital. So for this, it's 50%. And since a spherical orbital is closer to the nucleus, it's better able to stabilize the negative charge once the carbon anion is formed. So of the 3 hydrocarbon groups, the alkyne has the most acidic. And that's useful for us in building up complexity. We'll talk more about that today in terms of what types of bases are typically used. So for a carbon-carbon bond length across the series, it decreases because you're putting more electron density between the two carbon atoms. And then the bond energy increases. So we can think of the types of bonds that contribute to each. For an alkane, you have a carbon-carbon sigma bond. So that value is going to kind of carry through each functional group at 347 kilojoules per mole. When we get up to the alkene, we're now adding the contribution of the pi bond, which is 264. So the total bond dissociation energy of a double bond is 611 kilojoules per mole. Then for the alkyne, we have the second double bond, which adds 226. So the triple bond in total is 837. And so there's a correlation between the bond length and the bond energy. So there's two types of alkynes in terms of their classes. The terminal has the sp hybridized carbon H, and then the internal, these R1 and R2 groups are both carbon. So that's the acidic hydrogen that we're talking about with the pK of 25. So those are the ones that can readily generate the carbon anion. So we'll go through some nomenclature next and then look at some addition reactions to the pi bonds. So remember, in addition reactions, the pi bond is the nucleophile, that's the source of the electrons in the mechanism when we add across those two carbons. So each carbon atom of the triple bond is sp hybridized. That means it's supplying two sp hybrid orbitals that form sigma bonds, and then it has the two empty p orbitals that combine to form these pi bonds. And the pi bonds are orthogonal to one another. That means they lie on different axes. So instead of having just a pi cloud above and below, you have it to the sides as well. So it almost looks like a cylinder of electron density around the existing sigma bond. And so the main difference here is based on what electrophile is using, they can undergo double addition reactions. So all of the alkene reactions that we learned, these can basically do those and then just do it twice. So you do one addition, that's going to generate an alkene, and the alkene can then, if there's enough reagents based on stoichiometry, undergo it again. So our nomenclature rules, we take the ANE and then change it to YNE to name alkynes. So really the A to Y substitution is telling you there's a triple bond in the molecule. And then based on the chain length, there might be a number in front of that which indicates the start of the triple bond. So for 2 carbons, we have ethyne, which is also called acetylene. So some of these will have common names as well. For 3 carbons, there can only be a terminal alkyne, and that's propyne. So there's the terminal CH. And remember, for the terminal ones, that CH is acidic, so we can deprotonate it with a reasonably strong base. When we get up to carbon count 4 or above, now we can have terminal and internal. So here is where the number indicates the start of the triple bond on the longest chain. One change you might see on the final exam is how these names are written, where that number is located. I think the newer IUPAC rules put the number inside, like the parent name. I grew up with that, and I'm too lazy to change, so otherwise it's really the same thing. This is an example of, you know how Microsoft changes Word and PowerPoint every year or something? This is just an iteration of that. It doesn't affect your learning outcomes at all, but they just move the number in there. So from 5 to 6, at 6 you can see now, since the chain is longer, the triple bond can start at different places internally. The take-home message from that red line and below, any of these alkynes can be made from acetylene. So when you look at an alkyne and you identify the triple bond, you can dissect that molecule in 2 ways to do SN2 reactions. So the kind of substructure of that triple bond we see right here. And you can make dissections from either side of that triple bond, where you can generate a carbon anion here, and then whatever R1 or R2 is will be an electrophile with a leaving group, and then you can make any alkyne from this. So a table to show that. Let me just draw something here. So starting from ethyne, we have 2 acidic protons, so we can treat with a base to deprotonate one of them. That generates a carbon anion. So that's a nucleophile that can react with an electrophile. So nucleophile, electrophile, that's an SN2 reaction, and you've basically increased the carbon chain length of the alkyne. You can do the same on the other side and then make an internal alkyne. So to do this, starting from ethyne, if we wanted to make propyne, the electrophile that we could use is methyl bromide. If we wanted to take ethyne to 1-butyne, the electrophile would then be ethyl bromide. So with that, all the trappings of the SN2, rates, nucleophiles, electrophiles, solvent need to be followed. For an internal alkyne, so for 2-butyne, in this case, we would have to use 2 electrophiles. Both of them in this case would be the methyl bromide. When you get up to 2-pentyne, you can see that those electrophiles then have to be different. Any questions on that logic? So what bases are appropriate? Sodium amide, sodium hydride, and N-butyl lithium. So those are pretty strong bases that generate a conjugate acid that will not participate in any further reactions in the process. So the first step is acid-base. The second step is SN2. So what's important about acetylene, so the C2 alkyne? We talked a little bit about combustion when we were learning about stability of alkanes in terms of going from cyclic to acyclic. What does it mean to be strained? Combustion is important for taking a gas and generating heat. And so in this table, we look at the 2-carbon unit hydrocarbons from alkane to alkene to alkyne. Does anyone do any sort of metal fabrication? Have any relatives that do metal fabrication? So you can use these hydrocarbon gases and combust them to generate essentially heat, which can cut through metal. And in comparing the 3 classes, the alkyne is the one that's the most efficient for doing that. So in the combustion reaction, obviously the hydrogen count is changing for the 2 carbons present. But the number of moles of oxygen required are shown here. The reaction produces CO2, so that's constant. The other combustion product is water. So for each, they produce a different stoichiometric amount of water. If you take these 2 numbers and add them, you get this column. And then overall, this is the heat produced. And then we can normalize that number based on the total numbers of the moles of product. And when you do that, you see that the alkyne produces or is the most efficient for the number of carbons present in the moles of products produced. So an oxyacetylene torch, where you have a cylinder of acetylene and a cylinder of oxygen, the tubes are fed together into this Bunsen burner thing, for lack of a better word. I don't know what it's called. But you can spark it and adjust the proportions of each, and it'll create a really concentrated flame that you can cut through metal. So that's what is used kind of, I want to say, rudimentary or caveman. Nowadays, there's high pressure water jets that can cut through metal. If you've seen those are pretty neat. Also lasers, but this is essentially what is used in fabricating metal. Like a gas and fire can cut through metal. So all the stuff you learned in Gen Chem about solids, liquids, and gases, that's kind of neat to understand, even if you don't do it in reality. So that's another property of alkynes that's useful to us to make skyscrapers and stuff nowadays. So the reactions that we'll learn over the next couple slides, we've seen before with alkenes, but now the alkynes, again, they can do one addition that generates an alkene intermediate that may undergo a second addition reaction. We're going to start off with hydrogen. So hydrogen in a couple different flavors here. So hydrogenation, and the first example is total hydrogenation. So the alkyne is being completely reduced to the alkane. And that's going to require at least 2 molar equivalents of H2 gas. So typically in excess. The reaction is catalyzed by a precious metal, platinum, palladium, or nickel, and then a polar protic solvent. So with the H atoms colored in red, you can see that across the triple bond, we've added 2 equivalents of H2. And so experimentally, this is the reaction that's classically run to determine the degrees of unsaturation in a molecule. And that uses the Piv-Nert ideal gas law. You kind of rearrange that to N. Yeah. So you all thought I was going to use that for something. So that can measure degrees of unsaturation experimentally, and to do that, how many of you have actually worked with like a gas cylinder? Just a couple. So there's a regulator on there. Compressed gases are a little bit scary if you don't know what you're doing. There's certain types of male to female threads and stuff like that. You have to have the right one. Hydrogen's flammable, so you don't want to cause a spark that's going to make a torpedo that shoots through the wall. But otherwise, there's a primary regulator for the tank, and then the secondary regulator that comes out of that. And that's going to go into your apparatus, which you have to measure the pressure accurately so you can get that plugged in there. So this number comes out pretty accurate. So one thing I do want to mention is the next reaction is going to take these conditions but modify it a little bit. So total hydrogenation is going from 2 to 0 across that triple bond. A partial hydrogenation is only going to do one addition. So we're still using hydrogen gas, a precious metal, palladium on carbon, but now there's a poison called quinoline. There are other poisons, but This is an additive that will stop the hydrogenation at one stage. And this is commonly referred to as a Lindlar reduction. And so what, do I have it on here? I do. Maybe you can find it. What's the geometry of the double bond that's produced? So it ends up being a syn addition of H2. So you end up with a cis alkene. So you're always going to get a cis alkene out of that. So one thing you'll want to pay attention to, and we'll try to do some of this on Wednesday. When you have these sequences of reactions, especially cis versus trans alkenes, is this concept of stereospecificity of a reaction. When you have an alkene, you do an addition. How can you relate the relationship of the atoms in the product back to the starting alkene? Was it cis or trans? And so that ties in the mechanistic aspects. So to recap that, the syn addition gives you the cis geometry. So one thing to think about, which I won't answer right now, is how can you prove that you would have a cis alkene by proton NMR? So put everything that we've learned together over the past couple weeks. How do you know that an alkene is cis? What aspect of proton NMR would indicate that? So we can also take alkynes and make trans alkenes. Now, the conditions for this are a smidge different in that we're not using hydrogen gas as the source of the H atoms. We're using ammonia, so NH3. So we go from 2 degrees of unsaturation down to 1. And so this is also a partial hydrogenation, but overall it's called a dissolving metal reduction. So if you think of like the T-1000 in Terminator 2, the liquid metal robot who dissolves in fire, something like that. But you take ammonia gas, you condense it with a cryogen at minus 33, it becomes a liquid. From that liquid, you add in sodium metal. That metal will dissolve, and as it dissolves, the solution turns like this royal blue color. So what's happening is sodium is a group 1 element, so it has that electron that it gives up, and the ammonia basically solvates it. So you see this interesting color change to know that that part is happening. And then on the next slide, I'll show you mechanistically how the textbook presents it and how those H atoms get bonded in the trans fashion. So as with the prior slide, you might want to think about how can you know that an alkene has the trans geometry by proton NMR? So mechanistically, what happens, the sodium metal, the little naught sign means it's elemental sodium, so it has that extra electron. That electron we're going to think of as being nucleophilic, so it will add into the double bond. So it's a one electron movement. It's going to add into that unsaturation. So we have to then break a pi bond. And so those electrons in the pi bond will go on to a carbon. When it does that, it's going to put the radical and the anion in a trans relationship to minimize any electronic repulsion of the single electron versus the double electrons of the anion. So now that we have an anion, we can do an acid-base reaction with the ammonia. So that one hybrid lobe, that sp2 orbital here is still a radical. It's going to get a second electron from another equivalent of sodium. So we have another vinyl anion that does acid base. And so that will add the H2 across the triple bond in a trans fashion. At that point, it stops. So the alkene is not, say, electrophilic enough to accept any more electrons from the sodium to undergo further reduction. So with hydrogen or the equivalent of hydrogen, there's total hydrogenation, partial hydrogenation with Lindlar to give the cis alkene, and then the dissolving metal reduction to give the trans alkene. Any questions before we move on? So alkynes can undergo polyhalogenation. So in the example shown, if we use bromine, I've shown it step by step. If you can control the stoichiometric equivalence, you can basically stop at each kind of addition stage. Bromine in a non-participating solvent will add in the trans fashion. If you take that with excess, you add another equivalent of bromine. And so overall, you've added 2 bromines to each carbon atom. And so now you have this tetrabromo compound. So these are useful for many different purposes. One of them is, I think, fire retardant. So you can have these chains and then embed those in fibers of clothes to make the clothes fire retardant. There's other things shown here. One issue that's important nowadays, every generation has their scourge: asbestos, lead paint. Microplastics is probably your generation. I'm more of the lead paint. I didn't eat lead paint, I swear. There are other things that explain stuff, but persistent organic pollutants basically means these compounds, they don't have to be plastics, but organic compounds in general that get into the environment, and there's no like microbes or bacteria that will eat or metabolize them, so they just stick around. And eventually they get into the water table, they get into the soil, they get into your food. If you're male, they get into your testes. So they're in there, I bet you. So really, I think the issue is with those type of processes is the halogens. They, if an enzyme's going to come munch on this carbon chain, it hits that carbon with 2 or more halogens and it says, I can't do anything with this, and so it goes away and then the molecule just lives. So those are issues that are facing us as people moving forward in society that need to be addressed. So as the name states, hydrohalogenation, and I've rigged the substrate here to start with a terminal alkyne. We're going to treat that in this sense with HCl. That's going to undergo a Markovnikov addition, where Markovnikov states that the carbon of the unsaturation bearing the hydrogen, more hydrogens, gets the electrophile. And so the halogen traps it internally. And then you can repeat that process where the halogens end up on the internal carbon. It gets a little trickier when the alkyne is internal, because now you aren't following Markovnikov's rule. So what carbon atom of the triple bond is getting the hydrogen first is a matter of debate, and then that's going to lead you to a larger distribution of products. Any questions so far? So one last reaction here is oxidative cleavage. So if we look at the alkyne and slice it in half, each carbon atom of the alkyne is going to get oxidized to a carboxylic acid. To do that, we use ozone gas. If you take ozone gas and dissolve it in dichloromethane, it turns like a nice kind of baby blue color. You add your alkyne, that color will kind of go away, but as it's consumed. But when there's excess in there, you kind of know that the reaction's done because the blue color is persistent. Then upon workup, we're taking those carbon atoms and making carboxylic acids out of them. So think about what are the IR signatures of alkynes? How do we know an alkyne is in an IR? Also think about IRs of carboxylic acids. How do they differ from alcohols? Another one is the chemical shift ranges for sp hybridized carbons are different from sp2 hybridized carbons in the carbon NMR. So the ACS final exam typically does not give you any tables or references, so you'll want to have a general idea of where these things lie as you're approaching next week. Any questions? So we'll put some of this to practice with a starburst. And a starburst scheme basically has a central starting material, and then from that are just different transformations that the functional group can undergo, and you either supply the reagents or predict the product. So I think we'll start here. We'll just call this 1. So our starting material is a terminal alkyne, and we're going to treat that with hydrogen, palladium on carbon, and methanol. And so that will do a total hydrogenation. So from that phenylacetylene, we're going to make ethyl benzene. And as you review things again for the module exam and the final, think about how like the proton NMR is changing from this into that. So the ethyl group, that would have two signals in the sp3 hybridized region, a triplet and a quartet. So you'll want to review the neighboring group rule, multiplicity. So if we move around clockwise, we're next using chlorine in excess. So that will do a chlorination, and each carbon atom is going to get 2 chlorines. Another aspect of proton NMR to consider is the location of that hydrogen based on these chlorines. So remember that inductive effect where these heteroatoms are going to push a hydrogen signal further and further away from 0. In reaction 3, we're generating an internal alkyne. So from starting material to product, what electrophile should we use? Any guesses? So we're going to deprotonate that H with a base. That's going to generate a carbanion. And then we have to install those 3 carbons. So that terminal carbon needs a leaving group. So we could use propyl bromide to quench the carbanion and install the 3 carbons needed. That generates the internal alkyne. So we can take that, treat with sodium and ammonia. That's the dissolving metal reduction. That will generate a trans alkene. So now we've isolated an alkene. We're going to treat that with bromine in a non-participating solvent. So that's going to generate a 1,2 dibromo compound. Does anyone remember the stereochemical relationship of the 2 bromines? So the bromines have to add anti to one another. So we could represent it like that. So again, from the mechanisms, you want to review stereochemistry. What does it mean to have a stereocenter? How do you name stereocenters? Remember the polarimetry experiment with measuring optical rotations. So we're done with that sort of branch. Now we're over to 4 here. So reaction 4, we have to supply the reagents in the box. What's in the box? Notice that we're taking the terminal alkyne. We've added 2 equivalents of HBr, so this is a hydrohalogenation. That follows Markovnikov's rule. So reaction 5 is ozonolysis, so oxidative cleavage. We have two different carbon atoms of the alkyne. That means that 2 different products are going to be produced. So each of the colored atoms is going to go up to the carboxylic acid oxidation state. So benzoic acid and formic acid. That will likely get further oxidized to carbon dioxide and then bubble out of the solution. So a non-symmetric alkyne is always going to give you 2 different products. That's represented by the blue and green dots there. If the alkyne is symmetric, you're going to get 2 molar equivalents of the same thing. Question or step 6, provide the reagents, terminal alkyne to cis alkene. This was a Lindlar reduction. So Lindlar is going to give the cis alkene. So it stops at that stage. Then we're treating that with HBr. That's a hydrohalogenation of an alkene that follows Markovnikov's rule. So the H of the HBr will add to the carbon with the most hydrogens, and then the bromine traps it at the benzylic position. So in reviewing your mechanisms, you'll want to know, what's benzylic, what's allylic, what do those terms mean, carbocation stability trend, how Markovnikov plays into those addition reactions. So the starburst schemes or problems that you find in your textbook are a nice review of all those things. And then again, as you go through them, think about how you use IR, mass spec, and NMR to determine the identity of the product. Questions? So I brought a copy of this book. Hopefully you've been using it online. So I took some problems out of the addition chapter. We'll spend the remaining 15 minutes or so doing a couple of these. Just riff in it, see what we can see as a review of putting all this stuff together. So this is question 11.142. That's a lot of problems in that chapter. So it's asking you to draw out the mechanism and predict the product of this reaction. So we'll walk through some things. I'll point some stuff out in terms of getting to an intermediate and then what can happen after that and why one path would be preferred over another. So when I see a new reaction, one thing I like to do is just write out all the functional groups there, and that helps me make an association with the reactivity. So we have 1, 2, 3, a 4-carbon chain. There's a primary alcohol and then a monosubstituted alkene. We're going to treat that molecule with chlorine, which is an electrophile. And again, as you sort of land the plane here for the semester, you need to make those associations of functional groups with reagents so you know what mechanism is happening. Thus far, we've not really seen any reactions of an alcohol with Cl2. But we've seen reactions of an alkene with Cl2. So that's the first thing we want to do, is use the pi bond as a nucleophile and then the Cl2 as the electrophile. So we're going to do an addition reaction to form a chloronium intermediate, the 3-membered ring intermediate. So at this point, we have our reactive intermediate, which is electrophilic. In the rest of the molecule, we have this alcohol with 2 lone pairs. So that part's going to be nucleophilic. So we're going to trap that electrophile with a lone pair from oxygen. And we have 2 possibilities of how that can occur. So the blue numbers are from the nucleophile to an electrophilic site. The lone pair in oxygen can tack carbon 4 or carbon 5. So why don't you spend maybe a minute or two trying to predict the product from each of those? And then give me a short explanation of why one would be preferred over the other. So which path do you think would be most preferred? The oxygen at position 1 attacking which carbon atom? Four? Someone said 4. So let's just draw that product out. So next we'll draw the product of oxygen at 1 attacking 5. So those are the 2 possible routes from that intermediate. Based on examining the structures of those products, which one do you think is preferred now? So remember back to module 3 when we talked about ring strain. So 4-membered rings are more strained than 5. So the 5-membered ring is going to be preferred because it has less strain to it. So we can do a proton transfer, and then that will give us our final product here, this 5-membered ring ether. So really what this is, as we learned, it's an addition reaction where you have a nucleophilic group, which is the alcohol, embedded within the molecule. So instead of solvent trapping, we have the alcohol trapping it internally. And so we end up with that ether. So does that molecule have a stereocenter? So there's one stereocenter. We would get both the R and the S equally, so that would be a racemic mixture. So you can think about how would you determine there's an ether. Those are kind of hard. The halogen you would use mass spec for. Remember the signatures for chlorine versus bromine. Fluorine and iodine are a little bit harder to detect, but keep all that stuff in mind as you move forward over the next week. Any questions on this one? This is 145 in the second language book. You're given methyl, cyclohexane, and then this acyclic chain with a ketone and an aldehyde. And it wants you to provide the reagents that will carry out that transformation. So just kind of spitball in here. Can you name a reaction that we just recently learned that will produce carbonyl groups? So when we look at that and do a carbon count, so I'm just counting the number of carbons in that chain. Really I want to say red flag, but that's not the right word. The marker is that methyl group at position 1. So this methyl group in the product, when we trace back to the starting material, we see a methyl group there. So if I transfer those dots from the product to the starting material, there's where those dots would be. So in the starting material, those two carbons at 2 and 7 are connected. To get them unconnected and form carbonyls, that would be oxidative cleavage of an alkene. So in terms of like thinking backwards where that comes from, that has to come from an alkene where we've cleaved that double bond to oxidize those carbons to carbonyls. So the reaction conditions in the forward direction are ozone gas and dichloromethane. Then a reductive workup. So that's a tri-substituted alkene. And how do we make alkenes? We make them from elimination. So elimination, in this case, is dehydrohalogenation. So if we have a tertiary bromide with a small base, that will do the Zaitsev elimination, and then we can get the tri-substituted alkene. Then from that tertiary bromide, we get back to our starting material, and then what is unique about that has a tertiary hydrogen, and we know that from radical bromination. That's selective for tertiary hydrogens. So of all the unique sets here, the tertiary one gets substituted for the bromine. That's putting a leaving group in the right place based on the color of those carbon atoms. Which is then going to set the stage for an elimination, E2, if we choose the appropriate size base across those blue and green carbons. So from methyl cyclohexane, we can get to that 7-carbon chain with a ketone at 2 and an aldehyde at 7. So those are the kind of problems you want to be working on at this point. To put all this stuff together and understand the sequences. So Wednesday we'll do a little bit of review. You'll have your module exam Wednesday afternoon then.